Hey everybody, today what we're going to go through, you can see at the title, or at the top there, is geometric sequences. And so we've already done a walkthrough of what arithmetic sequences are. Today we're going to switch gears and start to look at a different type of sequence. You can see from that first statement, a geometric sequence is a sequence for which the ratio between consecutive terms is constant. So before we were looking at the difference between, today the ratio. So what does that exactly mean? Well, it means that each term is a constant multiplied by the preceding term. So rather than going and adding or subtracting from term to term, today we're going to be multiplying from term to term. What do we end up calling that constant? Well, this is called a common ratio for a geometric sequence, and it is denoted by R. So a little bit of vocabulary, a little terminology for us as we go. The rest of the day is going to be pretty straightforward, I hope. It's just us getting used to a new type of sequence and then playing around with some problems that deal with that sort of situation. Okay, let's jump in. If we're good that a geometric sequence is us multiplying by a value to go from term to term, then the way that we can find the common ratio is to divide any term by the one preceding it. And so what you see in blue on the screen is a very specific case. We could find R if we took term 3 and we divided it by the term that came before it, term 2. Or what you see in red would be the generic way that we could find R. That would be a general statement for us. That we could find R by taking any term, term n, and dividing it by the one that came before it, term n minus 1. So if we're having troubles trying to see how we're changing from term to term, then this gives us a way to calculate it. Okay, I think we've got everything at our disposal. Let's jump both feet in now. If we go through and we use some consistent language, that is, that for a arithmetic sequence, we used our first term to be represented by an A, then we will continue with that with a geometric sequence and have our first term be represented by A. There's no need to have a different value or a different expression to represent that. And now for a geometric sequence, we find that we have a common ratio that we'll denote by R. Then let's take a look at the red sequence. Our term term 1 would be represented by A. Term 2 would be A multiplied by R, because that's how we're changing from term to term. Term 3 would then be the term that came before it, A times R, multiplied by another R. And term 4 would be the A times R, multiplied by another R. And so if we take a look at what's been highlighted in red, then we should be able to simplify each one of those expressions into something that's a little more usable. That is, term 1 would be A, term 2 would be AR. We notice term 3 was A times R. That would then be AR squared. Term 4 would be A times R, which would be AR cubed, and so on and so on. And similarly, what we can do then is just take a look at how we go from term number to the expression for that term. So you will notice term 1 has no R's, term 2 has 1 R, term 3 has 2 R's, term 4 has 3 R's, and I'm hoping that that pattern is kind of screaming at you, that we might notice that every term has one less R than its term number. And so we could end up creating then a general term to say that term n has to be the value we start with, our first term in our sequence, then multiplied by a number of r's, and the number of r's is one less than our term number. And then what I just want to do is I want to kind of sneak in here a little bit that we just have a little reminder that n has to be a natural number. That is, it has to be a whole number that is positive. No decimals, no fractions, because it represents term number. I don't think we need to write out that a is the first term and r is the common ratio and n is the term number. I think that we should be good to be able to recognize that now as our general term for a geometric sequence. Okay, what I want to do is I want to jump in and spend a little bit of time just making sure that we're comfortable using that. So what you see on the screen, I have given you a sequence and I've asked you to find a and r. Now, if this was a test situation, like let's put ourselves in an evaluation situation, as soon as I told you in a question that there is an r, you can assume then that it must be a geometric sequence. That is, an arithmetic sequence doesn't have an r value. A different type of sequence that is not arithmetic nor geometric would not have an r. So as soon as I tell you that there's an r in there, well then that tells you it is geometric. So we should be using that then to guarantee that we find something that is geometric. Okay, for us to work our way through, I'm hoping we're trying to look at that sequence and pattern out what we have. And maybe we can say, okay, what do I multiply the first term by to get to the second term? Well, we notice that we changed signs, so I must have multiplied by a negative value. And what would you multiply 20 by to get to 10? You decimal junkies might say 0.5. My suggestion is let's work with fractions just in case some things become really ugly. So it looks like between the first two terms that my r value should be negative 1/2. Now what I'm going to do is I'm just going to confirm it. So now what do I do to negative 10 to get to positive 5? Well, it switches the signs, so I have to multiply by a negative. What do I do to 10 to get to 5? I've got to take a half of it again. And I feel pretty good that I've now found the correct r value. There is one way for us to be able to go through and determine that. Now, a little side note. Had this been an arithmetic sequence, my suggestion to you was to write everything with a common denominator. I just want to make a note here. When we multiply fractions, we do not need common denominators. We don't need the same size bits. And so you'll notice that's why I didn't go and write 20, for instance, as halves or fourths. I left it as 20, and I was just looking for what value I multiply by. No need for common denominators. Okay, let's backtrack a little bit, and let's say that purple was tough to come by. Well, maybe we go back and we use one of those relationships that we've already discussed, that my r value is any term divided by the term that came before it. And so if I'm having a tough time figuring out what that r is, then maybe I took my second term and I divided it by my first term. So if I took my second term, negative 10, I divide it by my first term, 20, I get my fraction. I notice that fraction reduces, and there we go. Now, one common, I don't want to call it a mistake, but one common problem we could face, that if you work through the blue, you might get into a situation where you miss a fraction reducing. I would argue for a lot of us that's less likely if we look and did the purple, if you were looking for the pattern. But obviously with the blue, that is a way for us to calculate it. Okay, We do have our R already taken care of. The question asked us to find the A. The A should have been a given because it is our first term. And so therefore, I'm going to just write out those values. There's my A value of 20, and I have now calculated an R value of -0.5. Okay, there we go. So we're inching our way along. We should now have the ability to be able to find a first value and determine our R value. Okay, let's move on to the next one. You see in problem 2, it says in each, the first 4 terms of a geometric sequence are given. So I notice in the problem, it already tells me what I'm dealing with. I need to find the general term and then find term 10. So we're going to work our way through A, and then I want to kind of leave you with B and see how well we do on B. If you're feeling super comfortable right now, then my suggestion to you is let's pause it right now and let's give A a shot. But if you want to kind of work your way through one together, we can go through now. So you make the call, pause it or keep going. Okay, I'm going to work my way through A. The first thing I need, if I'm going to come up with my general term, is I need my A and my R. So maybe, because we're starting to build up all these different types of relationships, I might want to write down, right off the bat, my general term is AR to the n minus 1. I'm going to drill that in by writing it down every time. Okay, up in my problem now, and I'm just going to move that down and create a little more space, I think. What I'm going to do is I'm now going to look from term to term. And we notice we multiply by 4, we multiply by 4. I'm maybe pulling out a calculator and just making sure in the last one, or maybe I can do a little multiplication. 4 40s is 160, 4 8s is 32, 192. Yep, checks out. I get a little confirmation. So I know my R value. I know my A value. I could build my general term. And so my general term is an A value of 3. And it doesn't matter whether you want to write a times by 4 to the n minus 1, put in that old-fashioned multiplication symbol. I happen to just put brackets around it because we've seen my R value could be negative, which means I'm going to need brackets anyway. So there's my general term. Okay, the problem also asked me to come up with term 10. And so now that becomes pretty easy for me. For me to find term 10 means I need to replace my n with a 10, of which most of you will not show me that. You guys will jump straight in on that. And yes, at that point, it really just becomes some button pushing. My suggestion to you, punch those buttons in following BEDMAS. Don't just blindly trust your calculator. So calculate 4 to the exponent 9, then multiply it by 3, and we should get a nice small number of 786,432. There we go. So we met the criteria for the problem. We came up with the general term in red, and then we came up with term 10 in orange. Okay, I think that process for us should have been pretty straightforward. I'd like you now to give B a shot, okay? So let's pause the video, and we'll come back, and we'll see how we match up. Okay, pause it now. Okay, we're back. So I have to come up with the general term. Again, write it down and drill it in. Term n equals AR to the n minus 1. Okay, now I've got to take a peek at all my properties of that sequence. Well, right off the bat, I can see that I have an A value of 5. But my R value, I'm going to have to do some work on. So you are either taking a term and dividing it the one that came before it, or you're taking a look and you're saying, okay, what would I do to go from term to term? Well, you do notice that you're changing signs from term to term. So that means I have to be multiplying by a negative value. You'll also notice that 5 becomes 10, and 10 becomes 20, and 20 becomes 40. So I'm multiplying all my tops by 2. You'll then notice on the bottom that I have 1 becoming a 3, 3 becoming a 9, 9 becoming a 27, and so I'm tripling all my bottoms, my denominators. I just found my R value. I'm multiplying by -2/3. As I said, you can always calculate it. So if you wanted to, we could find term n, and maybe I go like, I don't know, let's take term 3 and divide it by term 2. So maybe I'm going to take 20/9, and now I'm going to divide that by -10/3. Well, right off the bat, I'm going to have a lot of people that will say, you know what, I actually kind of like writing it with the old-fashioned division symbol because it may make it a little easier for us to flip and multiply. I would hope that we would do a little cross-reducing. And so you take a peek at it and you notice that 10 and 20, I could divide out a common factor of 10. My 3 and 9, I could divide out a common factor of 3. And so now when I multiply those together, I have my 2 times my -1 over my 3 times my 1, and I calculate my R value. As I mentioned, either way is okay. Okay, now that we have that information, now we can build our general term. It's a 5, and this is where we will not write this. There is so much wrong with that. First off, you have your double sign. That is not good. So we would require brackets. But also when you take a peek at it, please make sure that we recognize that the way that that is written, the exponent n-1 only applies to the -2 and not the denominator. So we're going to need brackets around all of that. That's why I mentioned before, why not just get used to writing it with brackets and then you're good all the time. Okay, there's my general term. Now I'm good to be able to go through and find term 10. So hopefully we matched up to that case or to that point. Now I can go through. I would hope for a lot of us, we can come right in on that. And we're going to notice a couple things. Well, first off, let's make sure that we follow BEDMAS. So we cannot do that times by 5 until we've applied that exponent of 9. Now what I'm going to do is I'm going to calculate that, or I should say simplify that. So probably again, I'm going to end up pushing some buttons. Like that is, we should know or be able to figure out what 2 to the 9th is without a calculator. Like I'm hoping we have 2 to the 5th memorized. That's our 32. And then we can just keep doubling and getting up to the point where we get 2 to the 9th. But I imagine we're going to push some buttons. There is our -512 on top, and you'll notice I have my negative because I know that my exponent is my exponent is odd, which tells me that my simplified value will still be negative. And then on my denominator, I'm going to calculate 3 to the 9th, and I get 19,683. Yes, our numbers started to get big. I'm just going to clean up that bracket. Now, the reason why I said leave the 5 out and don't try to do it all in one go, we should have been able to, if I write just on the previous line, see that we're not going to be able to cross-reduce. That is, my denominator is going to be made up of only 3s, like 9 of them to be specific, but it's only 3s. So when I see that a value of 5, I already know that I'm not going to be able to reduce my fraction. You will be able to tell before you even look at calculating those powers whether you'll be able to reduce or not if your a value has a common factor with the denominator of your r. So I got to that point in my orange. Now I should be good to just take my 512, multiply it by 5. There is my negative 2,560, and there is no reducing that fraction. There we go. Okay, you'll notice that in our geometric sequences, because we're multiplying by the same value all the time, these numbers are going to get really, really big, or potentially really, really small. We're going to be dealing with some much uglier numbers than maybe what we did with arithmetic sequences. Okay, we got to that point, and I'm hoping that we're pretty comfortable with a lot of this stuff. Now I think it's time for us to start working through some of those quirkier problems again. Okay, let's try one of those. Okay, you can see the problem on the page, and I think we're at the point where I think we want to start trying all of these problems on our own. So you give problem 3 a read, and then I want you to pause the video, and hopefully we'll come back and we'll see if our solutions match up. Okay, pause it now. Okay, we're back. Now, for some of us, maybe we weren't that confident to jump in. We were a little unsure what the question was asking. I'm hoping we're good, given that we've dealt with problems like this with arithmetic sequences. Determine the number of terms in the sequence, and there is our sequence, and we notice at the end of that sentence, we've got a period. So we know that 1,280 is the last term in that sequence. And so a little reminder from a previous day that if I was to write that this is term 1, this is term 2, term 3, term 4, I don't know how many are in between, term n could represent 1,280, and that would tell us then what number 1,280 is in that sequence. Okay, that might have given you a bit of a hint. If it did, then I want you to pause the video now and try to finish off the problem on your own. Okay, pause it now. Otherwise, we're going to work our way through and we're going to go through and solve it. So for us, we know that we've got this generic term. Our general term is AR to the n minus 1. Now, actually, this really brings up a good point. I should have never assumed what I just wrote down in blue. That is me segmenting my knowledge and saying, no, but I already know that I'm working with geometric sequences because that's the title for today. And that's not preparing me for what I'm going to need down the line. So I really actually want to get rid of that. I need to figure out what type of sequence this is first. Well, every sequence has a first term, so for me to find a equals 5 really didn't help. But then what I'm going to do is I'm going to look and see how do I go from term to term. So say this was a test situation. And I went, hey, I just subtracted 15. Now I just added 30. Okay, it is not arithmetic because I see that I'm not doing the same thing from term to term. I could then blindly go through and try to see, is it geometric? But there is something here that maybe should tip me off and allow me to recognize there's no way that it could be arithmetic right from the get-go. I have a positive value, then a negative value, then a positive value, then a negative value. And so if the terms in my sequence are changing signs from term to term, then there's no way that that is arithmetic. That is, I can't add or subtract the same value from each term and have it switch signs. Now, it doesn't mean that it's geometric. It could be something else. But at the very least, it rules out that it's arithmetic. And so it means I'm going to go on the hunt for geometric first, a little earlier. Okay, what do I do to 5 to get it to 10, negative 10? I need to multiply by a negative 2. I get a little confirmation on the next one. Okay, I now found that my R value is negative 2. Now I know that that is geometric, and so my general term is AR to the n minus 1. And now I can plug in what I know. Well, I know that 1,280 is the last term in my sequence. That would be my term n if I'm looking for the nth number in the sequence. So 1,280 is a term, the last term, in a geometric sequence that has an a value of 5 and an r value of -2. There we go. And you should really like what you have in orange. You take a peek at it, you notice that you have one variable, n. You can solve that equation. And this is where we really start to see some of the stuff that we've been working on come together. Look what type of equation it is. Where's your variable? It's up in the exponent. That means you have to get it out. We have an exponential equation, and so we can go through and solve that exponential equation just like we did in Unit 4. Okay, if I'm going to get it out, then that means I need a power equal to a power base the same. So that 5 that's sitting out in front, I need to get rid of it. I'm going to divide that out. And so if I take 1,280 and I divide it by 5, then I get 256. Okay, my variable's still up in the exponent. The way I'm going to get it out is I need to get a power equal to a power where the bases are the same. So I need to somehow figure out a way to be able to write 256 as a power base 2. Specifically, -2, because you look at the right side. Now, there is a couple things that I can use to help me out. I have not spent any time trying to memorize 256. What is 256 as a power base 2? But if I am able to solve this problem, then I have to be able to write it as a power base -2 because I know that my n has to be a whole number. Well, I can also tie together that if my base is negative, then I can only put even exponents on it to turn that into a positive value. So as I'm going through like maybe my guess and check process, then I'm only going to check even exponents on 2. And so maybe, let's just say I'm blindly going, hey, I don't know, what about 2 to the 6th? And I go, oh, that's only 64. I'm not going to try 2 to the 7th on my calculator. I would jump and try 2 to the 8th because I know I'm only looking for evens. And I notice 2 to the 8th is 256. And so there's the next line, a power equal to a power where the bases are the same, and therefore my exponents are equal. Remember, you have to write that line in, one exponent equal to the other, and now we can solve, and there we go. So what did we find for that problem? The number of terms in the sequence, there's 9 of them. What does that 9 represent? Put in your units, and you can go terms, and we are good. Awesome. Okay, hopefully we matched up. Otherwise, we figured some stuff through as we went. Let's try another one. Okay, you give problem 4 a read, and same thing. We should be working now towards can we problem solve our way through some problems that we are unfamiliar with. So I want you to try to pause this one and see if you can solve it on your own. Give it a shot, pause it now. Okay, we're back. So similar to a previous problem, maybe if I'm trying to get a sense of where I am within this problem, I know that term 3 is 12. I don't know term 4, I don't know term 5, but I know term 6 is -96. And then I don't know term 7, and I don't know term 8, and I'm looking for term 9. So that's what the problem's asking me for. Can you find term 9 in a sequence that sets up that way? You'll also notice that the problem told us that it is geometric, so I know that I have to be multiplying to each term. Okay, I want to walk through 2 different ways to solve this. The first way, I hope we would go back to our base definitions. That is, that we know how to come up with any term. Rather than using term, let me just get rid of that. Rather than using term n equals ar to the n minus 1, we may start being comfortable to say, well, if I'm looking for term 3, then I know that that has to be ar squared, 1 less r. Term 3 is 12. I could do the same thing with term 6, and I know that that would be ar to the 5th, and that's negative 96. Now, what we just created is something you've created a million times, but I'm going to argue to you, it might be likely you have never built that type of system. So I've labeled both of those equations as equation 1 and 2 because we can solve that system algebraically. Okay, up until this point, I think for most of us, we may want to go through and rearrange one of those equations. That is, like maybe you end up taking, I don't know, equation 1 and saying, well, A would equal 12 over r squared, and you could now sub 1 into equation 2. I think that that is a much better decision than taking equation 1 and solving for r, because now, that is so ugly for us to sub in. That would be a case where I think we're a little bit of a substitution junkie, and I would hope that we would maybe fight the urge. However, if we were going to use elimination, up until this point, the only operations you've been able to do between your equations have been add or subtract. And you will notice that if I was to, let's say, take equation 2 and subtract equation 1, I don't even care what's over here. I have unlike terms. So I'm not going to be able to collect those, and I won't be able to eliminate a variable. And so adding or subtracting between those two equations doesn't become useful at all. But maybe we can see that if I was to divide those those equations, I could actually eliminate a variable. Okay, I'm going to take equation 2 and I'm going to divide it by equation 1. I'm going to write this line in. I would never have to see it. You could just go ahead and do those calculations. There is me taking equation 2 and dividing it by equation 1. You'll notice when I divide them, my common factor of a divides out on the left side. And so that left side simplifies to r cubed. Nice, I just eliminated my variable, which was the whole point. Now I can take my negative 96, divide it by 12, and get my negative 8. And that becomes a pretty quick equation for us to solve. Yes, you could write this line in if you wish, but I would hope that everybody would just find the cubed root of negative 8, and there's our negative 2. Okay, nice. Now, I want to sidestep a little bit, and I just want to talk about how else we could have come up with that r value. We could have, up in our original, focused in on the 12 and how we move to negative 96. And we could have said that I would have to multiply by an r to get to the 4th term, multiply by another r to get to the 5th term, multiply by another r to get to the 6th term. And so maybe we would have looked at that, and we may have come right in on that really I'm going to take 12, multiply it by those 3 r's, so multiply by an r cubed, and that has to get me to negative 96. And you'll notice that we kind of come in on the same purple equation. Your next step would be divide out the 12. And now we can take the cubed root of negative 8 and find our negative 2. Just a different way to get there. It's algebraic as well. Now, one of the issues becomes, if we're looking for term 9, if I do the green, then I still have a little bit more work to do. Like imagine that this was an instance where I wasn't looking for term 9, but I was looking for term 900. Well, if I create the system or use the system method, then once I know what my R value is, for me to answer the problem and come up with term 9, I now actually have my general term. Like my general term right now is, I don't know what the first term is. My second part is R times my n minus 1. For me to go through and find term 9, I'm now dealing with this. It's not as useful. I don't know what A is. So I need to either backtrack and figure out what A is, or if I used my system method, I can now just sub R equals negative 2 back into one of my originals. Well, if I do that, I'll just sub it back into 1 because the numbers are easier. That's an A times 4 equals 12, and very quickly I come up with an A value of 3. Okay, now that I have that, I should be good to actually answer the problem. Let's find term 9. So my general term for this sequence is 3 times my R value, all to the n minus 1. And so to come up with term 9, I need to calculate that. Not too bad. So again, I'm going to follow BEDMAS, not trust my calculator. You can go through and just get your final answer. You don't have to write down 3 times 256. I don't need to see that. All of that is just pushing buttons. And so if you come straight in on a 768, then you are good. Nice. Okay, hopefully we got down to that and we're feeling pretty comfortable with it. Let's try one more. Okay, I'd like you to work your way through and try to come up with a solution to problem 5. Okay, we should be fully equipped to be able to tackle problem 5. So I want you to start straight from there and come up with a solution, and we'll see back if we match up. Okay, pause the video now. Okay, we're back. So we start to take a look at this, and it looks pretty similar to the previous problem. I'm not even going to write out my sequence. I'm going to say, well, this first one could create equation 1, and this second term could give me equation 2. And so if I use that first term, term 3, I could say that AR squared has to give me 45. And I could then say AR to the 6th has to give me 3,645. Now I notice that I have multiplication in between my variables on the left side. So for me to get rid of those, I'm going to have to divide them. And again, I'm going to take equation 2 and divide it by equation 1. When I divide them, my A's are going to divide out. I could come right in on R to the 4th. And then I got to do a little calculating, and I got to take 3,645 and divide it by 45, and I get a value of 81. Well, again, you can show me this, the 4th root of 81, but this would be an instance where I hope we'd be pretty quick to calculate it and get an R value of 3. Now that we know that R is 3, we want to go through and figure out what is our A value. And so I am going to sub R equals 3 back into one of my originals. Equation 1's got the smallest numbers. That means A times 9 gives me 45, and I find out that I have an A value of 5. Okay, I'm thinking we would have a lot of people that would get down to that point. And here's where I want to stop you for a second. Because we've made a mistake. And it is going to be by far the most common mistake that you guys make when dealing with these problems. I want you to take a peek at your solution and see what color on my screen where I made the mistake. If you're looking for calculation errors, I would argue to you, I haven't made a calculation error. I would probably argue it's been a theory mistake. Okay, what I'm going to do is I'm just going to write out that sequence again. And I'm going to do what I said I wasn't going to do. Term 1, term 2, term 3. Term 4, term 5, term 6, term 7. And then on and on. Okay. Maybe you can see the mistake now that you can see the sequence. Okay, if not, then I'm going to go through and say, if I took my shortcut, I'd multiply by r, I'd multiply by another r, I'd multiply by another r, and then I'd multiply by one more. You'll notice that I'm multiplying by 4 r's. Now, you get some confirmation in that in my purple equation, right? I have r to the 4th equals 81. There's my mistake. And it's not that I calculated anything. It's that I overlooked. I didn't consider something that might have popped up. Okay, I'm going to just erase that green circle that I put on so we can see my purple equation again. R to the 4th equals 81. I took the 4th root of 81, and I'm really hoping that you may have found that mistake when you algebraically solved. My R value isn't just 3, but it's plus or minus 3. If you recall, when I'm taking an even root, like a square root, I could have 2 possible answers, plus or minus. And if you look up at the top of your screen, if I get rid of all those little times by r's, and all I wrote was the sign, well, does it make sense that we could have multiplied by a positive, multiplied by a positive, multiplied by a positive, multiplied by a positive, and 3,645 would still be positive? Yes. But maybe now you can see, if I was to multiply 45 by a negative, by a negative, then my next term is negative. But if I multiply by a negative, then the next term's positive. If I multiply by another negative, the next term's negative. And if I multiply, because I have an even number of r's in there, my r value could have been negative, and I'd still have that purple sequence. That will be the most common mistake you make, is in not considering the positive or the negative. Now, the nice part is, when you solve that purple equation, you should automatically get your 2 solutions, because as soon as we take an even root, we know we get a plus or minus. So what does that mean for us? Well, it means that we could get the orange, but it also means we could get the red. That maybe what I do is I sub in an r value of -3 into equation 1. And when I do that, then I get my a times my 9 equals 45. And I notice that I get the same a value. I actually have 2 different possible sequences. I get in orange a sequence that starts with 5, and I multiply by 3 on every term, or I get in red a sequence that starts with 5, but I multiply by -3 from term to term. Okay, time for me now to go through and answer what the question asked, find term 10. So, term 10 in my orange solution, and I should probably just do this in orange, would be an a value of 5, an r value of 3, with 10 minus 1, so 9 in my exponent. In my red, my term 10 would be a first term of 5, an r value of negative 3, and 10 minus 1, so 9 in my exponent. Okay, you can already see we're going to get two different values. So you work your way through, you calculate that, multiply it by 5, and we get a 10th term of 98,415. Or when we multiply negative 3 to the exponent 9, shouldn't say multiply, but when we calculate negative 3 to the exponent 9, that's going to be a negative value. We could have also had negative 98,415. So be careful of that little quirky case. Why did it show up in problem 5 and not in problem 4? Because we had an even number of r's, or there was an even number of terms apart between the terms that we were given. Okay, something to look out for. Okay, there was a big topic for us today. Geometric sequences. Same thing as before. Now it's your job, jump in and get so much practice with it that you looking at the parts of those sequences just becomes automatic for you. We're going to jump in and we're going to start throwing all this stuff that we've been working on the last couple days together in the next couple days. So get enough practice to make this stuff automatic. Okay? Good luck.